A more appropriate way to determine the linear range is to use linear approximation. Plot your data as signal intensity on the y-axis versus the sample concentration on the x-axis, with the data points joined by a line, as in example 1. Then, starting at 0, 0, draw a straight line that is tangential to your data. Remember that a tangent line cannot cut through the data line or curve, but should only touch it, as in examples 2 and 3. If your data is concave in a downward direction, draw the tangent from the bottom, as shown in example 4. Here are some examples of the wrong way to draw a tangent line. Example 5 is wrong because the tangent cuts through the data line, which is not the true definition of a tangent. Example 6 is wrong because the line is not tangential to the curve. Example 7 is wrong because the tangent line is not drawn through 0, 0. After you have drawn the tangents correctly, examine each graph to determine the available sample load range. In linear approximation, the closer you are to the point of tangency, the closer you are to the true approximation of proportionality. The farther away from the point of tangency, the worse the approximation. So, you want to choose your region closer to the point of tangency. In this example, the tangency continues in a straight line past the 20 microgram and 30 microgram ranges plotted, respectively, in both graphs. In theory, you could then widen the linear range by extrapolation. However, extrapolation is not a reflection of or a replacement for real data. The best practice is to determine the mid-range of your actual data where the target and loading control can both be detected with a linear signal response. Use that as your starting point unless you know that your treatment has relatively large up or down effects on expression. The overlap of the two linear ranges represents your combined linear range. If you wish to use more data points to widen your combined linear range, then you will need to perform another separate experiment.